Hmm?
Hello, my name is Nick Demetta, and I'm going to briefly run through my section of this presentation on Chapter 13, overexploitation in populations, and the fuck me, dude. Okay, my name is Nick Demetta, and I'm going to talk to you briefly about the implementations of genetic conservation on overexploited populations, uh, as outlined in textbook chapter 15. So before we get into this, we kind of have to talk about what we're referring to when we say overharvesting. It's essentially hunting, fishing, killing, right? Killing of individuals in a population for the purpose of eating them. We'll see in an example here using their pelts, um, to such a serious degree that we are changing the genetics in their population. So, of course, overharvesting causes genetic change when we reduce the number of alleles in a population, take genetic material out. Obviously, we're going to promote things like genetic drift and allele fixation. And the first example that the chapter 15 gives for this impacts on exploited populations is in this Australian rock lobster. So this Melville Smith and Delestang population, done from 1970 to 2005, a short 35-year period on the carapace length, basically the size of Australian rock lobsters, kind of shows what happens when we overexploit a population, right? So we can see over that 35-year period, the size of these rock lobsters has significantly decreased, by a factor of about between 10 and 13%, 10 millimeters going from 85 to 74 millimeters on average. Um, and if you think about it, right, this is because we only take the big lobsters out of the population to hunt. There are legal requirements for the length of a lobster, uh, before you can harvest it, 76 millimeters. So if you find a lobster that's 76 millimeters or less, you got to throw it back. And the thinking behind this is that the smaller lobsters are not yet sexually mature, so they haven't passed on their genetics. So we throw them back so that they can make more baby lobsters, and we can have more to eat in the future. The issue is by only taking the large lobsters out of the population, some of those lobsters were not yet sexually mature due to mutation, and some of the small rock lobsters are sexually mature. So over a long period of time, we get more small lobsters contributing their genetics to the next generation, and the large lobsters are being taken out of the population. So we see that decline, in size, right? And this is, we'll talk about why that's bad in a couple slides here, but this is the first impact that the textbook describes. The next one is in maritime fish. Textbook focuses heavily on aquatic populations. Um, so we're going to be doing a lot of fish and lobsters throughout this presentation. Um, Another key concept to recognize is that overharvesting introduces a bottleneck, right? A bottleneck is a reduction in population size that causes genetic drift due to either human interaction or a natural disaster. Obviously, in this case, we're talking about human interaction. So in this study, 140 abundant maritime fish species were sampled, some of which were overharvested and some of which were not. And their genetics were compared, and the findings showed that overharvested fish populations showed a 2% decrease in heterozygosity and a 12% decrease in allelic richness. All this to say, when we're removing individuals from a population, we're taking their alleles out of the population, you have a greater likelihood of seeing homozygous individuals. And we're obviously like physically removing novel alleles from the population quicker than they can be replenished. Um, but we do see this discrepancy between the difference in heterozygosity and allelic richness. That's because allelic diversity is much more sensitive to reduction in population size. So, you have a population of, 15 billion individuals versus a population with 1 billion individuals. Um, on both of those scales, you have like tons of alleles for any given locus. So the odds that they'll be heterozygous is still pretty high, even if you've got a population that's been really overexploited and taken from numbers like 15 billion down to 1 billion. But we do see um, a, a significant reduction in allelic richness because we are losing a lot of those alleles. We just don't see that translated to heterozygosity because you just need two alleles for a particular locus to be heterozygous in diploid individuals like this. That's not to say 2% is insignificant. That's driving change, and that is ultimately contributing to a less genetically viable, genetically resistant population in the subsequent generations. But we do see less change in heterozygosity than allelic richness. Okay, now we're going to talk about unnatural selection, and we're going back to the rock lobsters for this. Unnatural selection is essentially, we don't just exploit a random portion of these populations. We're not like randomly sampling lobsters to take out of the population. We want the big ones, or we'll see in the next example, we want a specific phenotype that is often preferred in nature, or not preferred, but it's often advantageous in nature when we consider natural selection and sexual selection. So in the case of the rock lobsters, it's good for them to be big because they can fend off predators easier. They have bigger claws. They are harder to fit in the mouth of a predaceous fish or whatever, and they can off-put more sperm or eggs. They can produce more offspring, and obviously more viable offspring because their offspring will be big. But when we take large lobsters only out of the population, right, there are fewer large lobsters left, more small lobsters reproduce, so the population overall becomes less viable in the long term. So, and then there's the little rock lobsters from the B-52s. Yeah, so I referenced this example with foxes. These are foxes that were hunted, or this is a paper on foxes that were hunted, the red fox, in the early 19th and 20th century. Um, Hunters preferred to harvest the silver fox, the silver morph of the red fox. Can I don't know if you can see my mouse, but I'm pointing to this line at the bottom that's got a negative slope because hunters preferentially kill the silver fox because its pelt is softer and it sells for more money. So just a 3% bias in hunters to kill silver morphs over the crossbreeds and the red morphs. So if the hunter's out in the wild, statistically is only 3% more likely to kill a silver one. That actually caused over 100 years a threefold decrease in the genetic proportion of the homozygous silver morph and a 30% increase in the homozygous red morph. Um, so you can see just how much that small but unnatural preference for one phenotype over another can change the genotype of a population. And therefore, of course, we've reduced heterozygosity as well, which has, long-term viability implications. Um, yeah, not cool. This is a little flow chart that was included in the textbook that kind of sums up what we've talked about so far. Starting with human harvest, obviously we change phenotypic frequencies and mortality. Both of those can be explained by the rock lobster example. Increased mortality because they're smaller, and of course that's a change in phenotypic frequency. Modified natural selection, right? Those small rock lobsters are naturally selected against because they're easy to prey on and they don't produce as many um, offspring, sexual selection, and then earlier maturity, right? This results in reduction of frequency of genetically desirable or phenotypically desirable individuals, reduced genetic quality, obviously reduced heterozygosity and allelic diversity, which changes population dynamics. Um, the last topic that I cover for this chapter is spatial structure. It's a little bit harder to explain in terms of aquatic species because when we talk about spatial structure, we're talking about different populations, right? So if I was to explain the difference in harvesting in terrestrial populations, it's a little easier because they're geographically diverse, right? Whereas fish, they there's really no geographic barriers in the ocean. They swim everywhere. They interbreed a lot. Um, Distinct populations are hard to find. But with this example in the book, we're talking about um, two species of salmon, right, that are swimming. I should first explain the fishery portion. So there's a fishery upstream in a breeding ground for salmon. So salmon come from the ocean up this stream to lay their eggs to spawn. But this fishery has nets to catch the salmon and to eat them. But there's gaps in the nets. I don't actually know how big this is, but say they're this big, right? Younger salmon that are not yet sexually viable, or they're just phenotypically smaller, can fit through the gaps in the net and escape. So the smaller salmon are able to make it all the way upstream and spawn, and then they don't pass the fishery going back out. So they just go back out to sea. So the small fish are selected for in this example. And where we see spatial structure have an effect is say we have two populations of salmon. We have a population that's living in the ocean 500 miles away from the fishery, and there's one population that's only 50 miles away from the fishery. So when the salmon start their migratory cycles, the fish that are only 50 miles away from the fishery are going to get there first. They're going to get there, I don't know, say a month in advance, and most of them are going to be smaller, regardless of what their genotype is or how big they are when they're sexually mature. A lot of them don't have time to mature enough to be caught in that net. So more of those fish are going to escape through the gaps in the fishery nets and then go back out to the ocean, or they're going to go spawn, and then everybody's going to make it back out to the ocean, except the really big salmon and the really, yeah, or the whatever. And then the population that's 500 miles away is going to take a month to get there. More of those individuals are going to be larger, sexually mature, and there's going to be fewer individuals that pass through that net, spawn, and then go back out to the ocean. So we're disproportionately reducing um, genetic variability in that population that was 500 miles away just because of where it was, not because of a specific phenotype we're looking for. We're looking for big salmon one way or the other, but because it was in a different geographical population, we're disproportionately harvesting more of them. So it's obviously going to have different, obviously those two populations of salmon are going to be impacted differently because of it and have different genetic viability in the long term, right? And this graphic is just, it's not comparing two populations. It's just showing that because of the impact of the the salmon are getting smaller. The portion of large salmon are decreasing, and they're becoming there's more that are becoming sexually mature earlier, right? Okay, that's all I got.